Hello, dear colleagues, and it's my pleasure to be invited to give a particular lecture on this event. Collecting paradoxes is my hobby because I believe that understanding situations where the intuition fails helps to improve professional skills. And here I will talk about unexpected stuff in probability and field theory. I believe that it's very important to understand cases yourself, so I will move quite quickly. And I want you to download the slides and consider the interesting cases yourself. I believe it will do you much good. So let's begin. Assume that you have some sort of, say, investment, some sum of money, and every day you either win 10% or lose 10%. So with equal probability. You toss a coin, you either get 10% or lose 10%. It can be any alpha, but fixed from day to day. The question is, shall you be ruled after a decent number of tests? So the naive answer is yes, because we know that if the probability is 1/2, so approximately 1/2 of the games will be won, and the other half will be lost. So, and if you win one game and lose the other, you lose money. And vice versa. If you win and lose, you also lose money. So, after a decent number of games, you will lose money and lose everything. But this is an if answer. What is the strict correct answer? The formally correct answer is no, because if you use induction, you can easily prove that the expected sum of money after n games is 1. If it was 1, it remains 1. So, the theory says that you will not be ruled. Let's try a simulation. I use the R language here. And here you can see the trajectories of 4 guys who played 2,000 games, and all of them are ruled. The green one is a lucky one, and the black one is quite unlucky, but anyway, they all are ruined. So it seems that the naive answer is more correct than the correct answer. If it's a paradox, what's its solution? I was not aligning my talk with the previous talk, but the key answer is rare events, because rare events is often a source of the paradoxes. The reason of this paradox is very rare lucky trajectories. So theoretically, it's possible to win 1,000 games in a row, and it would give you enormous sum of money. And the symmetrical case, when you lose 1,000 games in a row, give you 0. The same 0 as if you lose 100 games or 50 games, it will be almost the same 0. So you have a huge amount of zeros and very rare, very large sum of money. And if you take the average, you will get 1. If you look from this perspective, you will be surprised why it is 1, or not 2, or 3.5 or something, just 1. But so it is. If you cut off long games, for instance, you restrict yourself by 1,000 games, you will get drastically less. So that's the solution. Let's consider another paradox based on the same idea. The well-known Saint-Petersburg paradox, when you toss a coin until you get a head. And if you get the first head as toss number n, you are paid 2 to the power of n coins. And what would you pay for one single game? To says if the pay is decent or too high, you need to evaluate the expectation of the random variable. And if you do that, you will get infinity. Because theoretically, you can gain the first head at any cost. And if you have it at cost n, the probability is 2 to the power minus n, and the payoff is 2 to the power n. They cancel each other and you get 1. So you get the sum of infinitely many ones, and it is infinity. So it seems that you must want to pay any cost for just a single game. But I believe that none of us would. Why? So the answer is, again, very rare events. And another reason is because the funds of the house is unlimited. So even if their funds are very, very high, so say 10 to the power of 15 coins, if you calculate expectation in this case, you will get just 51 coins. And if you play with your friend who has not more than 1,000 coins, the decent pay would be 10 or 11 for one game, which sounds reasonable. But theoretically, you can win 1,000 games in a row, so you will get ahead at top number 1,000, you will get all money of the users. But that's, practically speaking, that's not possible. So the same idea plays in the next paradox of expected number of games. Not a paradox, but strange result. So you play with your partner in the game of tossing a coin, and you either win or lose 1 coin at each game. And you play until one of you is ruined. Either you get all the money or he gets all the money. So you have A coins and he has B coins. The questions are, what is your probability to win? And what is the expected number of games until one of us is ruined? And also, if you play with the house, so with unlimited funds, what are your probability and the expected number of games? So, here is a very beautiful math used, different equations. Here are different equations, but we jump to conclusions. The probability is quite expected. It is your funds relative to the joint funds. So, and it comes to 0 if your vis-a-vis funds are unlimited. That's quite expected. You can't ruin a house. However, the expected number of games turns out to be A multiplied P. And this is not expected, because if you have 1 coin and he has 1 million coins, the expected number of games is 1 million. However, you lose everything on just the first game in 1/2. That was. And what is even more strange is that this expected number of games tends to infinity if you play with the house. So the conclusion is like that. You shall be ruined without any chances, but never. But in this situation, I will not rely on the average. Okay. So now let's switch from coins to a more complicated stuff like dice. So you toss 2 dice. What is the probability to see 9 together, 9 and 10? Are they equal or are they not equal? So the basic theory says that they are not equal because 9 is produced by 4 events: 3, 6, 6, 3, 4, 5, and 5, 4. Right? 4 events out of 36. And 10 is produced by just 3 events, so its probability is lower. And this is the correct answer. However, if the dice are completely identical and they are thrown simultaneously, and you are not able to distinguish C6 and C3 because you just have two identical dice. So it seems like you have two events in both cases, 6-4 and 5-5 for 10, and 3-6 and 4-5 for 9. And the total number of outcomes is 21. So from this point of view, these probabilities seem to be the same. Why this answer is not correct? Well, the first one is correct. Okay. The reason is because the ordered pairs are equiprobable. The theory of the basic theory of probability is based on the assumption that the elementary outcomes are equiprobable. And if they are not, so the theory goes wrong. The ordered pairs of dice are equiprobable due to symmetry. It's quite simple to understand. But the unordered pairs are not equiprobable. And that's the reason of this paradox. This paradox is very simple, very basic, but it turns out in more complicated, more hidden ways. You know, when you assess probabilities, you need to be very much sure that the basic outcomes are equiprobable, like this way or another. Okay, assume that you have 4 different strange dice. You play with your partner with different dice, and one die is considered stronger than the other if the probability to win is more than 1/2. So if you win more often than lose, then your die is stronger than his. So the first die contains 2 6 and 4 2s on its sides. And it is stronger than another die which contains 3 5s and 3 1s. It's very easy to check that the probability to win is 2/3. Yes? But the second die is stronger than the third one, which contains 2 zeros and 4 fours. The probability to win is also 2/3. Die number 3 is stronger than die number 4, which contains only number 3 on all 6 sides. One would expect that the fourth die is the weakest of all, because transitivity. But transitivity doesn't work here because the fourth die is stronger than the first one, with the same probability 2/3. If we compare the other pairs, we will learn that die number 2 is equistrong with die number 4. The probability to win is 1/2. And die number 1 is a little stronger than die number 3. So if you are to choose the die after your partner, you can always win with probability 2/3. If you are forced to choose the die first, you choose number 1, provided that the partner chooses randomly. You are expected to win. So this is paradox of transitivity, which tells that transitivity is also intuitional property, is not necessarily working for stochastic inequalities. Okay, now let's switch to politics. Assume that you are the governor of an island and you are supported by only 10% of the population, for instance, the army, and the other population is not supporting you. And you can organize the elections in several steps, but you are not allowed to press the people. They need to vote as they please. And you want to win the elections. How is it possible? We have only 10% of supporters. Well, you separate the island into 3 districts, and each district is separated into 3 regions. Each region is separated into 3 subregions and up to some level. And you divide your army into halves and put them into districts. And among the district, you divide the army into parts and put them into regions and so on. And you see that the proportion of the army people increases. So, at some level, the army would be more than 1/2 of the population inside the lower level regions. And there you will win. So you will have 2 out of 3 electors favorable to you. So you will win the next level elections, next level elections, and the top level elections, and you will remain the governor. So here is the picture. The red is the initial distribution of the army people among the regions. So you will win in each red tiny square. Then we make the next tour of elections, next tour, and the final tour, and you are the winner. It's quite unexpected, but so. This argument is very near to the counter set. The counter set from the theory of sets, where you remove the middles of the segment and you remove all length and you remain with the set of content. Okay, another political paradox. Can a parliament take any decision that its head desires? So the head of the parliament can assess questions, and the parliament votes for or against the question, and either approves it or not. The result is that the head can make the parliament take any decision he desires, provided that there is no complete majority that agrees on all questions. If such majority exists, so this majority rules, because this majority takes any question they please. But if there is no such majority, the head of the parliament is the one who rules, because he can force the parliament to take any decision desired. So let's see how. All the accepted proposals can be numbered. They're countable. They can be numbered and denoted by A with the index, and let M with the index be the set of the parliament members who vote for A. So, by B, we denote the joint proposals A1 and A2, A1 and A2 and A3. A and is purely logical operator. So, the number of guys who vote for B1, B2, and so on is an intersection of M1 and 2 and so on. And the intersection would decline. So, as we have assumed that there is no majority that agrees on all questions, this intersection will become minority at some step. And here comes the paradox, because they approve A1, A2, and A3, but they do not approve A1 and A2 and A3. And this is logically a contradiction, logical contradiction. So now the head of the parliament would propose A1, A2, and 3, and then this joint proposal, not B, 3 or C. And it will be approved by the rules of logic. So now any court would consider that all A's contradict not B, so the only way to do is C. and C is anyone the head wants. So the parliament can be forced to accept any law its head desires. And it's, well, it's somehow disappointing. So let's go back to coins, because politics is a bit dangerous, disappointing. So assuming that you toss in a coin, producing a sequence of head-tail, and you wait for 2 heads in a row. And your partner waits to the sequence head-tail in a row. What would come first? Again, there is a naive answer and a correct answer and the more correct answer. Yes? So the naive answer is that they are completely symmetrical, so the expected number of tosses up to any would be the same. The simulation supports this assumption. Here is the result of the simulation, 1 million games. The average number of tosses up to head-tail is 299, and for head-head it's also 299. The difference is in the 4th digit. However, if we apply the theory, we would get another result. The expected number of tosses up to 2 heads is 6, and up to head-tail is only 4. Here is very beautiful equations that give us this strange answer. The reason why the theoretically correct answer doesn't agree with the practically correct answer is because of rare events. Because it can turn out that you get 1 million heads in a row, and that won't do for head-tail. Okay, now let us switch to the game theory, just to do it a favor. You are playing such game, you and your partner, and your partner hides a coin, valued 10 or 20, something, and you guess. If you guess correctly, you have the coin, and if you fail, you pay 15 units of your loss. Is the game fair? It seems that it is fair because well, you expect that you will win, you will guess correctly in 1/2 of the cases, and it would be between 10 and 20, which is 15. But in fact, it is not fair, provided that at least one of the partners follows the correct strategy. So the game is for that one who is hiding the coin, and he wins 5 to 12 on the average per one game. And he needs to choose a coin randomly with probability 7 to 12 for lower and 5 to 12 to higher. And your best strategy is to guess randomly with exactly the same probabilities. So that's it. The game is not fair. So the last paradox for the day is the pirate's game, which I was giving talk on Monday. Now let's return to it again. The pirate's game is very well known for the quorum of 50%, but it has very interesting generalizations for any quorum and any crew size. So the problem is as follows. The crew of size n is linearly ordered, so each pirate has his deputy, except for the junior one. And the top pirate, called the captain, offers a share of a large amount of coins, sufficiently large, and this share needs to be approved by a certain fraction of the crew. Q is the fixed number called quorum, a fraction of parrots that need to approve the share. If the share is approved, then they share, but if not, the captain is excluded from the crew. His deputy becomes the new captain and makes his own offer. So we would expect that the captain would share the treasure in this or that way fairly, offering something at least something that at least depends on the treasure. But that's not the case. The classical problem for 50% solved by induction shows that the payoff does not depend on the treasure. The captain gives a lowest possible amount to 1/2 of the crew, starting from the third. So the deputy, who is always greedy, will get nothing. So this is all very well known. Let's consider what happens for lower quorums. It's quite clear. If you need less than 1/2, you can give nothing to some of those marked by 1 on the panel. So you have some freedom of choice. What is strange here is that for higher quorums, you also have some freedom of choice. And the Q equal to 1/2 is the only exception of this rule. You always have some freedom except for 1/2. So assume that the quorum is between 0.5 and 0.6. Here is the first few cases. If there are only 2 pirates, the captain needs to offer everything to the junior. But then he can manage with lower amounts. Look at the underlined case of 5 pirates is the strict case. It will do for 0.6, but not for any higher. So that's why we have the limit of 0.6. And then at 7, the crew of 7 pirates, the captain has some choice. He can choose 1 guy out of 2 marked by the question marks. Because he needs only 1 vote, he has 2 pirates. So he can offer 2 coins to only 1 of them. So, and if we proceed, we can prove by induction the following pattern, which depends on the visibility on screen. And provided that the crew is more than 6 pirates, the captain always has some choice. And you can imagine that this choice can be used for negotiation. You can promise this one to give him, he votes for you, and so on. But that's completely another problem. For higher quorums, between 0.6 and 0.625, the payoff pattern is slightly different. The captain needs to pay as much as 3 coins at some stage underlined, but later not more than 2. The pattern also depends on the visibility on 3, and the maximum payoff is only 2 coins. So the same way of reasoning holds for even higher quorums, from 625 up to 2/3. So now the payoff depends on the visibility on 4. The maximum payoff is 3 coins. The captain has some choice, and the total payoff does not depend on the sum of money, treasure they have, only on the position of the pirate within the hierarchy. One would guess that for even higher quorums, higher than 2/3, that won't work anymore. But no, it works. If we continue, we need to make a new assumption that if the captain offers everything to the junior, the other members of the crew would agree with that, because otherwise they would face the same problem. But if the crew is sufficiently large, the captain doesn't pay too much. We can trace the first few cases and see that at some stage, the captain is able to give nothing to those who would expect much and repress them all. And then the pattern proved by induction is quite regular. For more than 2/3 is like that. Depends on the visibility on 4 also. So we have constructed such patterns for different values of Q up to 0.9. So even if the captain needs 90% of the crew to approve his share, and the crew is large enough, he pays not more than 10 or 11 coins to some of the parts, and fewer coins to others. And this must work. The pattern looks quite complicated, but it depends on the visibility of some number, and it is very easily calculated. And due to this freedom of choice that the captain has, the pattern remains stable within some segment, some interval. Because for higher Q, you need to choose more guys out of 5, for instance. For instance, the quorum is between 0.5 and 0.6. For 0.5, you can choose 1 out of 3. For 0.6, you need to choose 2 out of 3. But the pattern itself remains stable. And these intervals condense near 1. If you are near 1, you have very short intervals, but the general idea remains the same. So, for instance, for Q more than 2/3, you give nothing to 25%, so you can manage to get 75% of the quorum. But you need only more than 66. So we have much freedom. If Q is 90%, it's still like that, because you give nothing to 1/11th, but you need 1/10. So you still have some freedom. This is a very strange and unexpected result. And the average individual payoff is estimated by the number y minus Q inverse, which grows, of course, as Q tends to 1, goes to infinity, but not as quickly as one would expect. So again, we came to politics. If somebody is offering a share, you better not expect to be offered much, and you will agree to that. So thank you. It was my pleasure to talk.
Thank you so much. Please address any questions if you have. Does anyone want to ask any question? You're welcome. Well, if not, then I ask one. So I guess that is completely a different problem, but it would be interesting to see if the hierarchy matters much here. So what if the pirates are not ordered in hierarchy? So there is only the captain and there is a group of pirates that are voting for some share. Do you have any intuition behind that? What would happen?
Completely, I think the answer would be completely different.
Yeah, that's the guessing, but no intuition. What will be the answer, right? Okay, because this...
I would not trust my intuition.
Yeah.